Okay, now gradient vector field. Gradient vector field is important vector field. It's a vector field that by definition is obtained, suppose capital F is a vector field. Suppose that this vector field is in 3D, depending of x, y, z, and you obtain by compute the gradient of the function f. And the function f is a scalar function. Right. Capital F is vector field. Little f is a scalar. A scalar, of course, multivariable function. Okay. The formula, let me recall, the gradient is partial derivative f with respect to x, comma, partial derivative f with respect to y, comma, partial derivative f with respect to z. Let's see one elementary example to understand a gradient vector field. Suppose that one function, a scalar function, is given x comma y comma z is equals x cubed times z plus y times z squared. They want to find the vector field. Well, okay. I want to find the vector field associated with that function. We compute separately partial derivative with respect to x is 3x squared z, and this do not depending of x. Partial derivative f with respect to y, no dependent y here, and dependent y here is c squared, and partial derivative f with respect to c. This is x cubed plus something plus 2 yz. Okay, therefore our gradient vector field x comma y comma z is equal angular bracket 3x squared c comma c squared comma x cubed plus 2yz. Okay, now we study in detail the important property for the gradient vector field. Okay, let's study now the property for the gradient vector field. It's also or always conservative. New word, conservative. What means conservative? Conservative means that the word done at the closest curve is 0, then the word between 2 points do not depend of path. Okay, let me translate in English this idea. Let me recall first what is work. Work in physics is a dot product between force that displacement is a vector, dot product. To understand this, I suppose the vector field is formed by the gravity. Suppose this is the gravity. The gravity always is a constant, regardless the position, and is also point down gravity. This gravity is a force, force, acceleration maybe, but it's a force. It's okay. It's the weight gets mg. It's a constant depending on the object, the body. But for example, we can find the word done in one closet curve like that. When you travel Entonces I want to analyze the work, but the work done by the vector field, no? Okay. So when you travel in this direction, look, it's a dot product. The displacement S, I indicate using the blue color, and the force is down. So it's the same, the angle in between is 0. That means that the work is positive. Makes sense, right? Because the gravity go for in the same direction. So it's in the same direction. Here, in this segment, the displacement is 90 degree displacement vector, 90 degree with the gravity, force of gravity, and the work in this case is 0, and this segment is 0, 0, 0. Like y here is 0 by the same reason, 0. However, when you travel in this direction, you go in opposite direction to the gravity, and the angle in between displacement and gravity is 180 degree, and the work is negative. So positive, negative, 0, 0. The work done in the closed curve is 0. And that means, let me put again the sketch of the gravity. Gravity is a beautiful example to indicate conservative vector field. Suppose I want to find the work done in between 2 points, 1 and 2. I put, for example, different trajectory. The work done when you travel in the straight line, in this trajectory, or in this trajectory. Okay? This direction, or this direction. Es obvio que in the closed curve, the work is 0. Therefore, the work done to do from 2 to 1 is completely independent of the path. Because suppose que I select this trajectory, I go in the opposite direction. This is 0. So the work done from 2 to 1 is one number, plus the work done from 1 to 2 is 0. Therefore, the work done to 1 is equal minus the work done to 1 to 2, que es obvio que es the same, 2 to 1. It's independent of the path we travel. The work is the same, independent of the path. In other vector field is not conservative, of course, this situation doesn't happen. But in conservative, yes. Therefore, we can define one potential function. Who is the potential function? Well, the potential function is a scalar, f(x, y, z), can define potential in any point. And using this potential function, we can compute the work done, because I know it's totally independent of the path. Okay? I promise that we see in detail in the last section potential function and work done in between 2 points. This is similar the student took before physics. You remember in the gravity we define the potential gravitatory energy, so the NGH, remember, right? This is the function f of x in physics. But in calculus you state relationship between these quantities now.